Hello people, welcome back to my channel. So hope you are enjoying the Python skill series. This is a different branch of Python skill series that we'll be discussing. This will be basically regarding the deep neural network implementation of the things we have learned so far. So based upon the ideas and the discussions about different libraries and different plots, so far we have discussed back in the previous Python skill series. So based upon that, what we'll be currently doing is like I'll start a separate series on building some neural network things. So we'll be taking few of the data sets from Kaggle website, and we'll be starting to analyze how we can do the things and build a neural network using the things we have learned so far. For that, whatever the codes and the data set, if it's possible or if it's not patent or copyrighted, everything will be put under my GitHub. So this is my GitHub, that is this one. So this is my GitHub, and everything about the deep learning will be put into this repository, that is Hitmonchan. And there are other repositories where you can find the other Jupyter notebooks related to Python. So this is the site, or this is the GitHub link from where you can find my uh, notebooks or the data files. So again, for this purpose, we require a data set. So I've considered or will be building a deep neural network based upon the Wines quality dataset, which is again taken from Kaggle. So I have my dataset loaded, and this is how the dataset basically looks like. So let's have a quick glance of what the dataset has to say. So basically, uh, this dataset has these many columns, that is type, fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, then pH, sulfates, alcohol, and quality. So this dataset is basically classified or characterized with the help of two categorical variables, that is white wine and red wine. So in the type you can see some of the values are white, and if you go down below somewhere you can find the type as red wine. So these are the two different classes, and you basically have 6498 entries, and somewhere you can see like this place you don't have any entries. That means there are some NaN values that will happen in your data frame. So it is your uh, activity that you need to drop those or do the missing value treatments of these NA values, else it will very much affect your deep neural network, and also you will get very poor accuracy when you do the run over this dataset. So these are the different metrics or the values when taken from a particular sample. So this is basically in the domain related to the chemistry. So in that you have different of these parameters and different values. So you get from that. So that is the domain knowledge required in order to do this. So again, I'll put the link of the Kaggle website from where I've taken this. You can directly download this dataset from there. Okay. So first what we do is we need to do basics of the pre-processing and basics of the summarization before we build our neural network. So as you can see, there are two subheadings. That is, first we are building a deep neural network based upon the Wines quality dataset. So in this we'll be basically doing all the summarization and the pre-processing that is required. So that gives a statistical evaluation of what we need to do. And the second part is about building the entire neural network. Okay, so let's jump on to this particular session, that is first one. So depending upon the collab version or Jupyter notebook if you are using, so make sure that you are upgraded to the latest version. So mine is the latest version. So if I run this particular TensorFlow version, we have 2.3.0. So that is the latest version it is using. And for building any deep neural networks, Google Colab has this particular setup that is for collaborators, mainly used for building deep neural networks. So you have this TensorFlow. So this is the library from where we'll be working upon or will be uh, building our neural network. So this is the framework that we have, and this is the LIS. So then if you want to check which version is compliant with your particular collaboratory, you can type this print command so that it will give you the version it is using. Okay, so that is regarding which version of TensorFlow you are currently running. So if you are using any older versions, some of the scripts or the code which you see in this video might not work. So that kind of things may be possible. So make sure you just upgrade to the latest version. Okay, so first what we do is we import two libraries, pandas and numpy. That is our basic libraries for any of the data analysis and processing purpose. And then we read this particular CSV. And in this, what I first do is I'll just remove this drop NA, and when I do the df, you can see the CSV file is converted to data frame, and you have 6497 rows, that is these many instances, and you have 13 different columns. Now, as I mentioned, there are some NaN values. As you can see here, you can observe there are some NaN values. So if you don't treat this NaN values at the beginning, what happens is that when you calculate the loss and the accuracy at the very end, when you go into this particular step, that is neural net building block, what happens is that you will obtain your accuracy as some NaN values or some empty values, which is not justified, or which may be a crap value. So you might not understand from where these things are coming. So in order to eliminate all those issues before you build your neural network, you first have to do the pre-processing. And so as I mentioned, you have many uh, NA values, not many, but there are few NA values. You basically do this drop NA. So with this, what happens is that you drop the NA values row wise, and then it will return the data frame. So now the data frame size has been reduced to 6463 rows and the 13 columns, whatever it has the original. So that are basically the columns or the dimensions which you have. Now let us do a basic check of D types. So these many attributes are present or columns are present, and these are the data types. So type is one thing which is the classification scheme, that is white wine and red wine. So that is in object, and rest everything you have in float 64, and there is one quality, that is integer 64. So based upon the class or the type, we can say here, that is white wine and red wine, we want to classify this particular data set, or we want, on basis of that, we want to build our neural network. So if we focus on the type, we check the value counts. So after pre-processing or after dropping the NA values, we have these many counts. So for white wine, you have 4870 entries, and for red wines, it is 1593 entries. Next, what you do is, uh, I want to have the red wines in a separate data frame and white wines in a separate data frame. So that is basically, now this one data set is containing both white wines and red wines. So I want to have a separate data frame which solely contains white wine and one which solely contains red wine. So that is just to make sure like these things which we saw in the pandas data frame, we are just using the same thing again and again. So just this is to bring to your attention that whatever we have studied so far, we are just using this, or whether it works or not. So that is for the basic thing. You can do this without running all these things. So let's check we are getting the right answers or not. So basically this is we are doing the slicing of the data frame, and it is based upon the type, and it will be on the red wine. So wherever the type is red, it will just put into a separate data frame. So that is all these. So basically the red wine portion is towards the end of your CSV file or the data frame. Similarly, for the white wine, if you run this, you have all the white wines that is proportionated at the top of the data frame. So it starts from 0. So this particular white data frame is consisting of all the white wines. So you have these many rows and these many columns. Similar is with the red wines. Next, what we do is we'll do a is null. So is null is basically it should return in every column, that is in every attribute, the same number of entries. So basically it has 6463. So 6463 is in accordance with this count. So that is nothing but after you do the drop NA, or after you treat for the NA values, you get that value. So that corresponds to all this count here, which you can see in each of the columns. Now our major problem is that if you remember the deep neural network, or if you have watched my videos on deep neural network, whenever I draw the neural network, I say like you have input layers, then you have hidden layers, that is dense layers, and then you have a one output layer, that is final one. And basically this type of classification, whether it's a red wine or white wine, those things are entirely on mathematical functions, or the activation functions which you use at each of these neurons are basically everything purely based on mathematical notation, whether it's sigmoid or tanh or Relu or leaky Relu or softmax or any other functions which you can mention. So now if you closely look, the type, which is the only column which we can consider here currently as our class, which separates these two data frames or data sets as white wine and red wine. These are the two classes we cannot directly put into our neural network, because these are object values. We can see the data type. Since we saw the data type of this, these were object, we can't directly uh, do the activity, or neural network can't be made to work on this type of data type. So what we need to do is we need to devise a method or find a way such that these two values, that is white or red, are converted to some binary values like 0 or 1 or something like that. So it would be much better that if you convert to a numeric value. So how do we do that? So for this particular thing, we have a special powerful method. I mentioned like you have to keep in mind every time whenever you do any kind of future projects in machine learning or deep learning, and that is based upon the or that resides inside the NumPy library, that is the where method. So we'll be taking help of the where method, and so its syntax is very easy. So again, this is just a small revision that we do from the NumPy. So what I do is I create a new column, that is a data frame column, to the original one. So it will be appended or created after this particular quality. So to this, what I'm writing is np.where, and where the type, if that type value is equal to red, then I'll assign a value 1, or it will be categorized as 1, and for 0 it will be categorized as white wine. So red wines, wherever you find the type as red wines, it will be classified as 1, and wherever you see the type of wine as white, it will be classified as 0. So if I just run this and if I just scroll a little bit here this side, you can see the target. So whatever was 0 here, that means it is a white wine, and these things towards the end, these are red wines. So now what we can basically do is we can just omit this type of this column type, and in place of that we have added one target column. So that doesn't make any difference to your data frame. So before this you had 13 columns, now these are 14 in columns. So basically you can just omit this, that is, this was the only non-numeric column which was there. If you observed from this dataset, rest all things were floating point or integer types. So we can now remove this type and we can start our working from this fixed acidity column towards our quality. So that was the major motive of this kind of pre-processing before you build a neural network. So now since we have done this, now we need to do or we need to check how the distributions basically look like. So for uh, plotting the distributions, what we basically have is we have a pair plot. So that will do the pairing of all the plots based upon the type of wines which we have and on all the different columns. So for that, I basically use the pair plot, which is from the Seaborn library, and to this I pass the data frame, and this is a parameter, that is kind of the diagram that we are going to produce will be a KDE diagram, that is the kernel density estimation. So if you remember, there will be a ribbon that is around the distribution, which is used to detect the outliers which are present and also to check if the two distributions overlap or not. And the hue, that is the color that I'm applying, is basically from the type column. So the distributions where you obtain after running this, those will contain two types of uh, colors. So one color will correspond to the white wine, and the other one will correspond to the red wine. So this particular command will take a little bit much time because you have 6463 entries. Yeah, these many rows which you have, and you have 14 different columns. So accordingly it has to plot. So the last plot which you get from this, that will be based upon the type of wine, based upon the target, that is this new column. So that will be not meaningful, but just for the initial purpose we'll do this. Or what you can possibly do is you can just trim the data frame from by using the ILOC or LOC from this to only quality, and then you can do the printing, that is just for these 13 columns, and then you can do the plotting. So it will be a very big plot that you get. So still it is running, you can see this particular cell, that is, it is still running. So because you have very few, or not very few, there are very large entries and you have many columns, so that's why it is taking some time. So the thing which you need to keep in mind when you do the plotting. So well, our plot is generated and you can see that very small portions, not even you can see, but you can see the distributions, but you cannot see what is there here. So for that, what I do is I just if I can change the color here, I'll change the color, and if I can zoom, that will be too much zoom. If you can see here, this is the fixed acidity, volatile acidity, citric acid. So it will by default remove the categorical column which is of non-numeric type, and it will basically plot everything, and the last one is nothing but the target. So just don't consider this particular uh, diagram or this particular scatter plot, that doesn't make any sense. So just when you inspect or visualize the pair plot, So you do the visualization along the diagonal, so that gives you the distribution each of how the type of the vines, how they are categorized. So there you can see like there is a significant overlap between two of these vines. So this is the portion that this particular shaded area, combination of this blue and orange, which you can see here, that is the overlapping region. Everywhere you can see that is there is a significant small amount of overlap. There is no perfect separation. Here you can see there is a very huge overlap among the two different types of classes. Here also that is the same, and here also. So there is no particular class that has perfect separation. And so if you noticed, when we ran this particular d type value counts, you can see that is there are some skewness present in the data set. So there is a highly imbalance that is present in your data set, which you can draw from this conclusion, because it's not equal. Means even after dropping the NA columns which were redundant or which were not meaningful, it still has some kind of skewness. So it can be also possible that before this there might be lower skewness, but this is what kind of thing we want to deal with. We don't want the values which have NA or which will lead to some crap values or unmeaningful results, but we are ready to deal with skewness, or we know how to deal with class imbalance. So we'll be moving with that basically. So that plot basically shows how the distributions are there of the two classes, whether there is a overlap or whether there is a perfect separation. Now this was everything regarding the data pre-processing and the data visualizations that we have done from the past 17 to 16 videos in the Python skill series. So for doing this, you require all those videos. If you don't remember any of these steps, I suggest you that you just watch the relevant topic again and again, and if you just missed anything in between, make sure that you just watch in one entire stretch. Don't skip in between, else because some of the points which we discussed in those videos you might have missed, because you might have clicked at the timestamps and just have ignored the discussions that we did. So by that you get more insights on this particular thing, how to look and so on. So I just zoom this out back. So now what we do is, now since we have done the data pre-processing and all the cleaning activities that we have done, we saw the visualizations, we know the skewness, how much distribution it is carrying, what are the distributions looking like. Now we go into our model generation. Now for model generation, especially in Google Colab or in TensorFlow, we basically use a framework that is called as Keras. So Keras is basically a library that will be used for neural network building. And just a brief reminder about this particular library, that is sklearn model selection. So whenever you build a model, you have to put a blueprint. So you have your training and test set ready. So in the data set, whenever you do the split, you split it into a separate portion, like that is a thing we have been discussing from machine learning. So based upon some prior analysis or your own analysis, you will do the partition of your data set into training set and test set. So in order to do that, not manually, you can do it manually, but it will be a larger line of code than this what you currently see on the screen. It will be a larger line of code. You can make use of this sklearn.model selection, this particular library, and from this we are using a method that is train test split. So that is an inbuilt method which is present in the sklearn library for splitting the model. So it will randomly do the splitting internally. But there is one drawback with this particular thing which you do here, that is because it will introduce some kind of data leaks. So some of the data set which are classified in red wine may go to white wine, or some of the white wines may go to red wine. This kind of things are possible because there is some kind of randomness that is involved. So let us see where it is observed, or where the randomness basically comes. So for that, first I want to do the splitting of my training and the test set. So first what I'm doing is, so I want all the records, that is all the tuples rows, and I want columns from 1 to 13. Now from 1 to 13, if I say, what I'll do is I'll just write a df, and if I print this, you can see like I don't want this particular column, that is this, so this starts from 0. We don't want that, so we start from 1 2 3 4 5 6 7 8 9 10 11 12. After quality we have target. So target we don't consider for train test split, because target is the thing that you want to predict. So tomorrow when new instance comes in, you want to predict the target, whether it belongs to a white wine or whether it belongs to red wine. So you don't put that into your target. So whatever my training data, that will be based upon this, that is from fixed acidity, this column to the quality. So only that portion will consider in my training set. So for that I have this positional based labeling, that is by using ilog. I want all the rows, and I want from first column to column number 12. So this will not go to 13, it will be n minus 1. Basic math is 13 minus 1 12. So from 1 to 12 columns you will basically get in this. So that result I'm storing in X, and then in Y what I'm storing is I want another split. So that basically is the syntax of how the train test split takes. So it needs two variables, so X and Y. And in X variable, what you put is basically all the columns which you have in your original data set, just removing the categorical column, that is the non-numeric column. And to the Y value which you, or the Y parameter which you pass on to the train test split method, in that you invoke np.ravel function, and to this you pass a df.target. Now df.target is nothing but your label, that is binary valued attribute which you have generated. So what Ravel will do is it will return a contiguous flattened array. Now this particular thing is done internally in order to optimize the processing when you build your neural network, or whenever you feed this train test split to your neural network, it has to do some kind of optimization internally for better efficiency, so that it will not take too much of the time for processing. So for that you basically run this np.ravel method. So this is one important thing which you have to keep in mind, that it returns contiguous flattened array. So I'll just do the dark theme again. Okay. So it will return contiguous flattened array. So it will be one after the other. So there will not be any intermediate space that will be opted. Everything will be flattened one after the other. And then what I'm doing is I'm doing a nesting operation which we have seen many times. So that is nothing but the x train, x test. So this particular x instance. So this is one instance, and this is another instance. So these two instances I now want to split into training and test set. So this will be X train. For this again will be X test, Y train, Y test, and all these things I'll be nesting and putting to the train test split. Now just watch carefully what this train test split takes into. That is the parameters, that is the X value, that is this one, the Y value, that is this one, that is the flattened array, and then you have a split, that is test size. So basically what we are saying is like the test set size which you have, that will be 30%, and the training set size, that will be 70%. So we just mention only one parameter, that is the test size 30%, 0.3 is 30%. So that will automatically consider the training set to be 70%. And then you have what we said before, that we have some randomness. So that is the random state, that is 42. So 42 is some random number which you just do for splitting. So in most of the neural network building, you have this number that is usually observed. So that is nothing but randomly it will put instances to the training and test set. So that will be random. So uh, it will be not that intelligent that everything will be put in white class separately and everything will be put in red class separately. It can be possible that some instance of red class may go to wine class and some of wine class may go to red class. So that kind of randomness is possible, and due to this randomness I said that there are certain data leaks that are possible with this kind of approach if you are doing it manually. So if you want to save your line of code, then you have to do this. Else if you want to do a manual way, that will be doing in some separate video, that will be a further few lines of code which you have to write. So that will guarantee very few data leaks, but this approach will have most of the data leaks. So that will also impact your accuracy. So we'll see each and everything, how it is affected, how model building is basically affected. So this is basically the random splitting into training and the test set. So if I want to see how many entries are present or what is the size of my training and test set of X and Y, if I run this, you can see that is the size, that is 54,288, 1,939, 23,268 and 4524. So everywhere if you see, the training set size is much higher, that is 54,288, and the test set size is very less. So in this portion, so that is the thing which we have mentioned with the help of the test set size, that is the 30% of the instances which together comprises, that will be split into this ratio. So this is the 30% of whatever you have in X that goes into the test set, and the remaining will be going to the training set. Similar is with the Y. Now if I just see a few of the entries in Y, that is y is nothing but this one. So that is nothing but our column, that is the target column, and so it consists of an array, that is n dimensional array. So that is basically used for faster calculation. So we saw whenever we do neural networks or whenever we build a neural network, we mainly have to use the array function or the inbuilt representation of an array from NumPy, because it has direct and faster executions. So that is the basis for this discussion. Just a few more minutes, because this discussion is going to be long, because we are building a neural network. Okay, so just hold on. And what we do is now, uh, we have another library, that is from sklearn. We have pre-processing. And from this sklearn.preprocessing, what we are doing is we are importing something called as standard scaler. Now what this standard scaler is, now what it basically does, so it basically will standardize the feature by removing the mean value and scaling to the unit variance. So if you see standardization, by default, or it's the de facto for requirement for any machine learning estimations which you do. So uh, if you have any bad features that will not contribute to your model, then more or less it will be like affecting the data or the accuracy at the end. So you will have larger loss and lesser accuracy, but you want the vice versa. So for that standardization which you want to apply, and when you go to model building, so before that you want to do all this pre-processing. So this is also one activity which is done in pre-processing, which we have not seen before. This is in context with the deep neural network, and so we are discussing here. So from this library we are importing this particular class, or we are calling this standard scaler, and we are then creating an object standard scaler, and to this we are passing the constructor. that is standard scalar, and to this we are calling a fit function, and in fit we basically pass the x train that we get from this split that we did above in this portion. So, and one more discussion, why standard? Because it basically does the standard deviation calculation internally. So all those math happens internally in the layers of the sklearn library. So you need not worry about that. And this particular standard scaling do not apply to the output variable. The output variable is nothing but your uh, this, that is the y thing. So the y train and y test will not participate in this kind of pre-processing because we don't want to do that. So the basis is like, if you just observe these values, that is 0.2730, you have different precisions, different decimal points. So there needs to be some normalization in the range of 0 to 1. So you need to do that thing for all these variables. Just you will exclude the target column because that you need to predict, so that will not basically participate. So for that we have just applied this transformation, that is the scaling, standard scaling, only to the x train and x test. So internally it would have converted into the range 0 to 1. So that is the basis thing which it does randomly internally. And so due to all these randomness, you will get different results when you do different runs with the different hyperparameters. So that will be discussing in the next discussions here. So this was all regarding the data pre-processing, data summarization, visualization, and standardization, normalization, regularization, everything which you want to say with respect to all your data. So you have splitted your data set, everything which you have done. So now it is in very flattened representations, contiguous memory which is there, and which utilizes less of your memory space as less as possible. Now having done all of these things, you want to start your model building. So now we go into the neural net building block. So this will be, from this portion or section will be generating our neural network. So the resultant of this discussion, or whatever you see the codes, will not generate anything like you have this neurons connected, those network thing you won't observe. Will be writing codes. So the output which you get, so that is a resultant of the concepts which we have seen in my deep learning playlist. So if you want to check that video out, you are free that you can check that video. So the resultant of the discussion will not generate any neural network uh, diagrams in fact, but it will be entirely codes basically. So first, before building the neural network, we want to have a blueprint of our model. So blueprint is nothing but a sketch, a rough idea, or an outline of where and what, how the things will fit perfectly. So for that we need to have a blueprint. So how will we draw that blueprint? So for drawing that blueprint, what we have is, we have this TensorFlow Keras. So Keras is a standalone library, or it's a framework which is uh, used for building any deep learning or convolutional neural network models. So you can use its inbuilt functionality in order to build any kind of deep neural network models, any neural network which is complicated. So from this library or framework, we are importing a class called as sequential. So sequential is one way to generate your neural network, and there are two ways basically, as you can read here. So the sequential thing which I took here, it is simpler, and there is one more variant that is functional, which is very much flexible or versatile. Means you can add more functionalities as compared to the sequential. Sequential is just you have the input layer, then the hidden layers in between, and then you have the output layer. So that is the simple model. So for that we go with the sequential, and then from TensorFlow keras.layers we import something called as a dense class. So this dense class is basically for adding the layers, that is the hidden layers which are there in between, not the input and not the output, but just the layers which is there in between. And then we want to use some advanced activation functions. So there is one library which has the basic activation functions and some advanced activation functions, and in advanced activation functions we need to use the Relu activation function. So for that we are writing this Relu. So if you don't know what is an activation function, I suggest you to check my deep learning playlist available on my channel. So I have covered all the most widely used uh, activation functions, and we have discussed about the advantages and disadvantages, why there is not a certainty about the activation function to use. So for building any neural network, at least you have to put any activation function. But the TensorFlow library itself is extensible, so you can write or come up with your own activation function if you wish to use. So I encourage you people to do that also, if you know deep mathematics and if you love to code with that math. Okay, so now since we have imported all these things which we require, we now will design a blueprint. So first we want the instantiation or the initialization. So for that we call the constructor of the class, that is the sequential, and that I'm putting into object or a variable, that is model. So this statement, when the compiler executes, it will statically create an empty model which will not have any weights, which will not have any biases, not neurons. We'll basically not use the term neurons, but we'll call them a units. So that is more appropriate in this context. And the weights in this particular example, or in this particular video discussion, what we are doing will be not manually setting the weights. So if you want to manually set the weights, you have np.zeros matrix or np.ones matrix. So with that you basically do the instantiation of the weights. But here internally in the Keras libraries, you have some inbuilt functionality for initializing the weights. So that is something called as Xavier methodology of initialization of the weights. So it is all done internally. These are the some extra stuffs that is uh, happening inside. So that is some extra discussions or extra knowledge that I'm giving. And then what I want is, I want the first input layer. So after the input layer I want the first hidden layer. So to add any layers, you basically call the add function, and to this add function will pass a dense function. So that is nothing but add is to add a layer, and inside that we will put a dense network of different units, neural units, neurons. So for that we call this dense, and this nodes or the number of units of these particular neurons will be 30. You can take any number, so I have just put 30 for the analysis purpose. Just we'll do any rudimentary analysis to check how our model performs on this data set. If the accuracy is not good, we'll change any of these parameters. So if you got this particular number, this is nothing but one hyperparameter which you first encounter in this. There will be many other hyperparameters which will be seeing forward. So after mentioning the number of units which you want or the number of neurons, you basically put the activation function that you want to use. For simplicity, we'll use the Relu. There is another version of leaky Relu that deals with the explosion of the gradients, if you know that concept. So we'll not do that, we'll instead stick to Relu. And then what I say is the input shape. So input shape is basically 12. Now why 12? Now this is not a thing which you do randomly. Uh, this 12 is because here in this particular thing we have done a split. So this split was in accordance with the data frame that we had. So we wanted from fixed acidity to the quality. So that returns 12. So we want to make our neural network work on these numerical columns, excluding the target, excluding the type that was categorical. So that's why we are putting this 12 here. So this will complete our first hidden layer, and it will have 30 number of units or neurons. And so there are no guidelines or any golden rule like to how many neurons to start with. Everything here is a hyperparameter. Uh, Next, what we do is we don't do here right now, that we'll do later. So that was basically adding a new hidden layer, so that we'll do later. So as I wrote here, add one at a time. So we'll add one layer because the computations will be too higher for all these instances to run. And then we want one output layer which will do our binary classification, and so it will basically work on this particular target column. So it will predict either 0 corresponding to white wine, and it will predict 1 corresponding to red wine. So we again write the same syntax, and to this we put the activation function and sigmoid. We don't put the input shape. Input shape is just required for the first input layer that is required. So if you remember, it does the forward propagation. So what the input layer has, it will pass on to the subsequent layer. So that's why whatever you add after the first layer, you don't put the input shape. So that is by default understood like it will have 12 columns. So if you understood this discussion about generating the blueprint of the model, now let's uh, consider all these things, and we'll see the model as an entire entity which is ready to build and which serves as a basis for our performance evaluation. So just stick for a few more time. I know this will be a very big video. So now what we do is, based upon all these things which we have computed here, so now what we'll do is we'll do a model dot compile. So this is another method which is present inside the Keras library. So it will be invoked upon the model. So model whatever you have here, that is the instantiation, adding the dense layers in between and adding the output layers. You basically do a compile. Now this compile has few parameters. So to this you pass a loss function first of all. So that is one parameter that you pass. So the loss function that we'll be using here, that is binary cross entropy. So binary cross entropy is nothing but the also called as log loss function. So log loss function, if you remember about the t-SNE distribution, it is basically used to find the difference between two separate distributions. So there we basically use that, and so since we have used a sigmoid unit at the output layer, uh, and also we have the target as 0 and 1, so we'll be using a binary cross entropy. So if you just wish to know, or if you want to know what the binary entropy function does, I'll put the link in the description. Make sure that you check that link. That is from the Medium website. That is a very good detailed overview of what this binary cross entropy is. And then what we have is we have an optimizer. So optimizer is one such thing which you want to apply to your neural network, so that any of the neurons which you initialized here, that is all the 30 neurons, it won't collapse in between. So for that you basically does an optimizer. So optimization is very much important when you have a very large dense network, and also very thousands and millions of instances. So there are other optimizers in the literature. So there are like SGD optimizer, RMS prop optimizer, then ADA delta optimizer, ADA grad optimizer, ADA ma optimizer, FTRL, then NADAM optimizer. So from that all of those will be basically touching the Adam optimizer. So all these optimizers have different functionalities. So that is a separate section that will be covering some part later. So for the time being, just remember, like, you have to use the Adam optimizer, and then we have the metrics. So whatever we calculate, we want to estimate the accuracy, how good that particular model will perform on my data set. Or if tomorrow I give any unseen instances or unseen new data set, any other random data set, how well it does the accuracy, or how well it does the classification. So all values, whatever you do here, this optimizer, name of the optimizer, the loss function which you apply, everything is hyperparameter. So uh, and the Adam optimizer which you apply, everything is the hyperparameter. The binary cross entropy is same as the log loss entropy, which is nothing but for used for KL divergence, that is for the T SNE. And then comes an important thing which is called as epochs. So epochs, when it comes to neural network implementation, epoch is one term that is defined here. So one epoch means the number of times you read the entire data set, especially your training data set for building your model. So this should not be confused with the term iterations, because iterations has different meanings. There are iterations within iteration, that is nested iterations. So iterations are something different. uh, the definition of epoch is given here, and somewhere uh, you want to do the early stopping, and that is a mandatory, because if you have two less instances, or if you produce any batch size that we'll be discussing later, then it will lead to overfitting. Also, if the number of epochs or the read of your training set is very frequent or very often, it may happen that the neural network will find it boring to read the dataset every now and then. Because of that, you can consider there can be an overfitting that your model will be facing. So these are the things which you have to keep in mind. So should not keep epoch too high nor too low, because if you keep it too low, that may lead to underfitting. And then what I have is I have batch size. So this entire data set of this 6463 instances, that is one huge humongous data set. So now your neural network will not take the whole of the data set into all its input layers. So for that, you have to partition the data set into multiple splits. So in order to partition into multiple splits, what you do is you do the batching. So you take few of the instances, say from 1 to 10, you have one batch, then 11 to 20, you have second batch, 21 to 30, you have third batch, and so on, until all the data set or all the entries gets exhausted. So that is mutually exhaustive. So if you just multiply all these instances, so that will constitute your data set. So that is nothing but your batch size. And then I have different instances of the batch size that I've done here. So that will be seeing how it will impact your model accuracy. So this is the entire thing that we are compiling. So I believe I have run this command and this particular command. Okay. And if I run this, okay. And then there is one particular command from the model, from the keras, that is a summary. So it gives the names internally by the compiler. So what it means, like if you run this, it will give you the type of layers. So there are two dense layers. So one which we are currently not using, because I have just done the commenting. So this first entry. So this naming is given internally by the Python compiler. So that you need not worry. What you need to check is like how many instances it is having. So 30 is the number of neurons it is basically having. That is this one. And then you have the dense 4. So it has only one entry. So that is probably your output layer, which is for the classification. And then you have all the total parameters, trainable parameters, non-trainable parameters, which are 0. So that is the summary or just a basic bill or receipt of what your model is going to be. So you have all these audits done before you deploy a neural network. So it is not a simple thing like you just create a model for classification. There are different things which you need to do pre-processing and stuffs like that. So we'll be covering everything one by one. This will be a very long video. So now in the next step, what we do is uh, I do the model fitting. So just mind you, like before you execute this model fit or you call the fit. So fit is nothing but your model construction will begin after this, and it will print for all the epochs that you have mentioned with all the batch sizes. So before this, if you haven't done any pre-processing or any of the slicing, it will severely impact your model and therefore your accuracy will be very bad. So to fit, what I'm passing is the training, why training, and the batch size I have batch size here taken as 50,000, so that will go here. The epochs, that is 40 in number. The validation split, so now here the split will be uh, based upon the training subset and the validation set. So if you know about the nested cross validation, so in nested cross validation we had this generalization error estimate. So there what we did is we had two kinds of loops, inner loop and outer loop. So in outer loop what we did is we splitted the data set into training and test set. But in inner loop the training set was divided into training subset and validation set. That similar logic is followed here. So you do the splitting again of this particular data set, especially the training set here, into 30%. So 30% will be going to validation set and the rest 70% out of this training set entirely will be your training subset. And verbose is one parameter that is used for the logging thing that will be seeing when we run this. And uh, I have written outlier analysis must be performed before execution of this line. And if you don't have any outlier detection technique which you have laid, you can either perform univariate analysis, or if by univariate analysis it's not visible any outliers that is there affecting your data set, you can probably do clustering approach. So that is one bonus which I gave you. And here in this, that is I am again doing the nesting. So that is the loss and the accuracy that I'll be printing after this. And finally I am calling a model dot evaluate, and based upon the fit that I'm doing on the training and the X train and the Y train, I'll evaluate its performance on the test set. So that is simple. So in coding terms, you write in this way, and verbose is equal to false means I don't want the logging of that. I just want the value how it is printed. And if in outlier detection, if you do a univariate analysis and if you don't find any outliers, or if you do the model fitting with the help of regression line, you don't find any outliers. These outliers are especially called as leverage points. So leverage points are very much important. So you have to identify these leverage points and remove this. These are outliers. So basically it requires the domain expert knowledge basically. So you want to check whether you want to put that or you should not put that. So those are leverage points we should keep in mind when building the neural network. And so this basically will be returning a training set and validation set. So if I run this, you can see that epoch is so that is one read of the entire training set. This is second read of the entire training set, third read of the entire training set. And the thing which you want to notice here, that is the loss which you are getting and the accuracy. And this is based upon the training set, and on the validation set, what is the loss and what is the accuracy, validation accuracy. So ideally, the loss should be less and the accuracy on both the training set and validation set should be higher. So accuracy, if I see like on the training set, I have 88% and on the validation, I have 86%. Now you can have different results depending upon how many epochs you have put, what is the batch size and things like that. So there are number of other parameters like the activation functions which you use, even that also matters in this value. So if you run this, you might get different results. So that is obvious. So you will not get the same results as you see in this particular screen. So the verbose thing basically does this logging kind of stuffs. So there are some particular meanings to this. So that is not visible in this particular run. That will be doing whenever we build a neural network on MNIST data set. So in that I will convey that meaning what this double lines and all has. So these are the time required to execute that particular epoch or that particular run. And the thing which you want to notice is the final accuracy and the loss, especially the accuracy. If someone asks what is the accuracy of your model, you basically have to say like on my validation set the accuracy is this much, and on the training set this is my accuracy. Now, well, this was the evaluation, that is the run we have made. Now what I want is I want to print all these things. So I'm basically calling this print history, and uh, I'll just comment this thing out. Okay. So basically what this command does is it will history. Now history, what does history consist of? So history consists of this model dot fit this value whatever it has, and it has the loss and the accuracy. So it will basically print the validation accuracy and the training accuracy. So if I run this, you get this array of values, or basically list of different accuracies from the run which you have made just above of this model dot evaluate. So model dot evaluate will give you the run basically. Now what I want to do is this particular will not convey any meaningful result unless we do some kind of visualization. So in order to do that, we'll basically do a box plotting. So let us see how that box plotting is done. So here I am converting this particular entity into a data frame, and I'm using pd.data frame. Now that will be one entire data frame that will be working with, and that is my training accuracy. And similarly for the second line, this will be my validation accuracy. So this should be a line above, else it will be a confusion. Okay. So first thing is my training accuracy and the second thing is my validation accuracy. Both are a data frame storing into two variables, TA and VA. And I'm just concatenating these two. So that is TA and VA and access is equal to 1 means it will happen row wise. So one after the other. So what basically I want to visualize is I want a box plot of two things, that is training accuracy and validation accuracy. It should be one after the other, that is next to each other, and to this I'm calling a box plot. So if I just run this, you can see this box plot which you have observed from your Cbond or matplotlib. So from that, so now our discussion is like what this basically convey, or this plot what basically convey, or when you show to your customer or to anyone, how would you explain this? So the thing which you can see on the x-axis, that is nothing but your accuracy, and the thing which you see here, these are the whiskers, that is this black lines which you can see here. So this is the lower range of the accuracy, that is if you look 0.418, so that is somewhat here, and 43, so that is characterized by the end of this whiskers. These black lines up and down characterize the end of the whiskers, and this box which you can see here, this part is the upper quartile Q3, the lower quartile, and the median value. So the middle value which you can see from this list values which you can see here, uh, the middle value is somewhat 0.7. So 70% is the average accuracy or the median value, and here also it is somewhat less than 70%. So these are the two things which you can make out of this, not just merely printing the values, but conveying it into a more meaningful results, which can be much more explainable. Now what I want is, I want to evaluate this entire thing based upon a confusion matrix. How much is my true positive? How much is my false positive, true negatives? This kind of analysis I want to do. So for that, I need to have true class labels and predicted class labels. So for that, I need to create a predicted variable. Now predicted variable with will be respect to my target variable, which we have done created. So that is the binary classification that we have, that is zeros and ones. So for that I have y predicted, and to that I have a method that is np.round. We have seen this method. So these methods are not new to you. So for that we have done this different sections of Python pandas and NumPy libraries. So we are calling a model.predict, and to this I'm passing my x text test. So basically on test data I want to predict that. So what is my accuracy? So for that I'm running this, and if I just do a slicing, you can see internally it has converted everything to float. So this is the peculiarity of the round. Whatever integer values it will have, it will convert everything to floating point. And now what I want is, I want to evaluate my loss and accuracy. So this is with respect to training, x train and y train, and you get the test accuracy, that is 88.3%. So that is the highest which you can observe here. So highest, if you just see here, that is the Q3 which you can see, that is somewhat above this line, that is the upper quartile. So that is 88.3, and this same thing, if you pass x test and y test, you have 91.3. So that is with respect to the test set which you have, and this is one way of to print this. So this is hard coded, you can do this, else it will not do the conversion internally, so it will throw some kind of error. This percentage 0.3f is basically for printing the precision values, and if you just observe this thing, these are nothing but the formatted string. uh, we have seen formatted print statements in the uh, printing for the value of quadratic equations. So in that we have seen this formatted print statement. So from that I've taken this. So small things there we have used in this building for the neural network. We are visualizing where how this things comes into picture. So now we have our test accuracy and the training accuracy. Okay, this should be training accuracy, and this is my test accuracy because I'm passing test. And then for confusion matrix creation, you don't have to do much of the coding. Just from the sklearn library, you import the matrix method or matrix library, and you call a confusion matrix method which is there internally. from this matrix object, and to this you pass y test, y predicted. So based upon the y values, that is the output values which you have, that is zeros and ones. So those are basically in zeros and ones. So you want to predict for the new instance or the new test instance which you have, which you pass here. So for this you will predict some values, zeros and ones. So that basically gives a measure how well your model performed, it's good or bad. Accuracy is one different story, and confusion matrix is on the unseen instances how well it performs. And the labels, so that is zeros and ones, that is nothing but our label which we have in our target column. And my confusion matrix, I want in the index, that is we have true class and predicted class. So in true class it will be white for white class, and for basically white wine and red wine. And in the columns I have white wine and red wine, it will be predicted. If I just run this, you have this confusion matrix thing. So this thing, that is 1353, that corresponds to true positive, this corresponds to true negative, false negative, and true positive. So whatever you see in the diagonal, that is this value and this value, this should be higher, and things which are there in the off diagonals, that should be lower in the ideal case. But due to there are some randomness or skewness present in your data set, there is not perfect separation. We have to do some more. So now let us do one small activity, whether we can get much better accuracy or not. So I have this batch size. So with batch size 5017, just 17 more instances to 50,000. I'll just do this, and I'll just run this thing again, and you can see the accuracy. If you just look here, it just got increased. So now you have 97% accuracy, and the validation set you have 96% accuracy. If you look at the box plot, it will look something like this based upon the values which you obtain. So there is a shift in the box of the box plot. And if I just predict this values, and this is my training accuracy and this is my test accuracy, and if my confusion matrix gives very few misclassifications or false positives and true negatives are present, but you have these values the highest as compared to the previous setting, because it depends on the batch sizes or some other parameters. Some may be jointly, if you put, it may have an adverse impact, so that may significantly impact your model accuracy and the performance. So well, we wind up this session, this entire big session of building a neural network from scratch, from the Vines dataset from the Kaggle. So hope you enjoyed this video. If you found you got educated about this video, please do like, share, comment, and if you are new to this channel, please consider subscribing. Thank you very much for watching this video.